Alright, hello everybody, and this will be part 3 of my Introduction to Calculus series. So in this video, we're going to be taking the ideas from part 2 of finding the gradient of a curve and come up with some kind of mathematical formula for it. So remember, our goal was to find the gradient of this curve right here at this specific point. But in order to find the gradient, we needed 2 points to be able to compare between. So what we did was we selected kind of like another dummy point that's also on our curve. And now that we have 2 points that are relatively close by, we can use our usual rise over run to find the gradient of a line that passes through both of those points like so. And remember, the closer we put these 2 points, the better our secant line here approximates the actual tangent line that we wanted to find. So let's take a look at this curve right here. I've called this function y equals f of x. So f of x can be any function, it really doesn't matter. So we're taking in inputs of x along our x-axis here, and then we're inputting the x into our function, and then whatever value we get out of our function here, it's going to be represented by a y value on our y-axis. So if the x-coordinate of this point we wanted to find the gradient of is, let's call this point x. So x can be any single point along the x-axis, it doesn't really matter. Well, if the x-coordinate is just, well, x, then what is the corresponding y-coordinate of this point? Well, just plugging x into this function here, we're going to still get f of x. So that means our y-coordinate of this point is just simply f of x. So I'll put the y-coordinate in right here, it's just going to be f of x. And remember, our dummy point here, this blue point here, will be some distance away from x. And the idea is we want to shrink that distance closer and closer. So let's say the x-coordinate of this kind of dummy point here is some distance h away from our original point x. So what will the x-coordinate of this new point be? Well, it's just going to simply be x plus h. So this is the x-coordinate of our dummy point here, and if we plug this point into our function, what are we going to get? Well, we're going to get f of x plus h. That means the y value of this point here is just simply f of x plus h. So let's just write down the y value right here, it's just f of x plus h. So you see, now we have the x and y coordinates of these 2 points right here. So what we can do now is finally use rise over run to find the gradient of our secant line here that passes through both of those points. So the gradient of our secant will be some rise over some kind of run. But what is our rise? Well, our rise is just the difference in y values between these 2 points right here. But what is the difference? Well, we're just going to take this upper value right here, which is f of x plus h, and then subtract this lower value here, which is just simply f of x. So this thing right here is exactly our rise. So our rise becomes some kind of f of x plus h, which is the coordinate of our dummy point here, and then we're subtracting the y coordinate of our original point to get the difference. So that's our rise taken care of. Now we have to find what our run is, but remember, our run we just defined it as h because these 2 points here are just some h distance away from each other. So our run is just simply h. So there you go. This thing right here will be the gradient of our secant line. But remember, the secant is just an approximation for the actual tangent line, which is this line right here, right on the red dot that we wanted to find. So what we want is for our h to be as small as possible. And the smaller it is, the better it is. And you may also notice here that h can't be 0, so the distance between these 2 points can't really be 0, because if you have 0 on the denominator here, then the whole thing's just going to... and that's not good. The idea is we want to see what happens to the gradient here. Remember, this whole thing here represents the gradient of the secant. So we want to see what happens to the gradient as our h gets very, very, very small. So we have to introduce some kind of new mathematical notation for that, because we don't want h to be some discrete finite value. We want to see what happens as h gets very small. So what we say is, what is the limit as h goes to 0. And to write that down, all we do is write lim for limit as h approaches 0. Because remember, h can't be 0, but to find the gradient of the tangent line, we need h to be as small as possible. So all this limit is doing, you can think about it, as pulling these 2 points in closer and closer and closer together. So we have the limit as h approaches 0 of the gradient of our secant, which is f of x plus h minus f of x. And remember the numerator here, that's just the rise, the difference between our y values. And then we have all of this junk divided by h, which is the run. And this thing right here, this is what we call first principles. Because it was kind of like one of the first formulas which really started this whole topic of calculus. And probably one of the most important things and the most innovative ideas about this expression right here is this limit here. Because what the limit actually does is it says, well, this thing right here, this f of x plus h minus f of x all divided by h, that's just an approximation for our tangent line. But we don't want an approximation, we want the actual tangent line. So we have to see what happens as our h gets smaller and smaller and smaller. So using first principles here, we can select any function of x we want, and we can find the gradient at any point x that we want. So in the next video, we're going to be doing an example of first principles on a specific function. But until then, I'll see everyone next time.